In the coldest ocean on Earth, a squid the length of a school bus hides in complete darkness. Its eyes are as wide as dinner plates built to catch light a human eye could never notice. Its body holds a chemical that lets it float for hours without moving a single muscle. Its arms end in curved hooks, ready to grab prey twice its size. Something bigger swims below it, hunting by sound instead of sight, carrying scars from squid that fought back and barely escaped. You're about to meet the colossal squid, the ghost squid that vanishes with a flick of its skin, and the sperm whale locked in a war with it that has lasted millions of years. If deep sea monsters pull you in, hit like and subscribe so more of these stories find you. Take a breath. We are heading down. The Southern Ocean does not ask permission. It circles the bottom of the world with nothing to block it, no continent, no long chain of islands, only open water wrapping around Antarctica in an endless loop. Waves here build for thousands of miles before they hit anything solid. By the time one reaches a ship, it can tower taller than a two-story house. Wind screams across the surface at speed strong enough to rip a tent apart in seconds. Sailors gave this stretch of water two nicknames, the Furious 50s and the Screaming 60s, named for the lines of latitude where the wind never seems to calm down. Ice drifts everywhere, some chunks small as a car, others wider than a football field, pale and almost invisible once the light fades. At the surface, the water sits close to freezing for most of the year. Fall in without protection and the body starts shutting down within minutes, not hours. That brutal surface is only the opening scene. Below the waves, the ocean drops into a darkness colder and stranger than anything happening above it. Sunlight fades fast. Pressure builds with every extra foot of depth, squeezing harder than a car crusher at a junkyard. Life down there has to bend the normal rules of biology just to keep existing. Most animals cannot handle that combination of cold, crushing weight, and endless night. The ones that can are not soft, timid creatures hiding in corners. They are hunters shaped by millions of years into something almost unrecognizable, next to their relatives in warmer seas. Among them are squid, and not the small kind served on a dinner plate. Some stretch long enough to lie across a school bus from front to back. Some carry eyes wider than a dinner plate itself. Some can turn from solid flesh into something you could see straight through, then flick back to solid in an instant. This is their world, a place humans have barely mapped, sitting at the edge of every chart, ignored by almost everyone except the scientists willing to send cameras into the black. Every year, that list of scientists grows a little longer. Every year they find something new down there, and every discovery makes the Southern Ocean feel less like the edge of the map and more like the edge of what we actually understand about life on this planet. Before we meet the giants waiting in that darkness, it helps to know exactly how deep, how cold, and how far from rescue this water really is. Because what lives in the middle of that black did not evolve just to survive here. It evolved to rule here, and the deeper this story goes, the less that sounds like an exaggeration. Rescue teams consider this stretch of ocean one of the most dangerous places on Earth to attempt a real rescue, sometimes needing days just to reach a stranded ship. A single storm here can last an entire week without one clean break in the wind, battering anything caught in open water without mercy or warning. Even satellites struggle to track every iceberg drifting through these waters, since so many break apart and reform faster than any map can keep up with them. Somewhere below the waves right now, something the length of a bus is drifting, waiting, watching for the smallest flicker of light. It has no idea a whale is doing the exact same thing, one ocean layer below. Picture your kitchen freezer, the one that turns water to ice in a few hours. Now imagine an ocean that stays close to that temperature for months at a time, stretching farther than the distance from New York to Los Angeles in every direction. That is the surface of the Southern Ocean. Go deeper and it gets even stranger, because the deep water here barely warms up at all, even in summer. Near the seafloor, the temperature can drop below the normal freezing point of fresh water, kept liquid only because ocean salt lowers the freezing line. Humans have walked on the moon more times than they have visited the deepest parts of this ocean in a submarine. Only a handful of remotely operated vehicles have ever been sent down here, and each trip cost more than most people earn in a year. There are no coastal towns nearby, no fishing boats passing by on a normal Tuesday, no cell phone signal within thousands of miles. If something goes wrong at these depths, help is not hours away, it is days away, if it comes at all. That kind of isolation changes everything about how life survives. Animals here cannot rely on a mate showing up nearby or food drifting past every few minutes. They have to be built for scarcity, for silence, for going long stretches without seeing another living thing. Pressure adds another layer to the problem. At a depth of about 1 mile, the water pushes down with a force equal to stacking 50 jumbo jets on top of a single square foot. Go deeper, toward 2 miles, and that number climbs even higher. A human body would be crushed instantly without a submarine's thick metal shell to hold the pressure back. Yet squid live here, soft-bodied and completely unprotected by any shell or exoskeleton, thriving in conditions that would kill a person before they even understood what was happening. How does a creature with no bones survive pressure that can crumple steel over time? The answer starts with the way these animals are built from the inside out, and it is stranger than most people expect. Their bodies are not fighting the pressure, they are matching it, letting the ocean squeeze through them instead of against them, using tricks no land animal could ever copy. It is the reason a squid can live comfortably at a depth where a submarine hull starts groaning under the strain. Even the research ships built specifically for polar work often need weeks just to reach these coordinates from the nearest port, burning through fuel and supplies before a single camera ever touches the water. Every hour of ship time down here costs more than most people spend on rent in an entire year, which is part of why so few expeditions ever get funded in the first place. Somewhere in that freezing, crushing dark, a shape longer than a school bus is drifting through water so cold it should stop a heart, so deep it should stop a submarine, and so remote that almost nobody on the surface even knows it is down there. Fish struggle in the deep southern ocean. Their gills work hard to pull oxygen from cold water, and their muscles burn energy fast just to fight the current. Squid solve that same problem in a completely different way, and that difference is exactly why so many species of them thrive down here while other animals stay closer to the surface. A squid moves by pulling water into its body and blasting it back out through a narrow tube, shooting forward like a tiny rocket. This method costs very little energy compared to swimming with fins and a tail. In a place where food can be scarce for weeks, saving energy is not a small advantage. It is the difference between surviving the winter and starving before spring. Squid also grow fast and reproduce in huge numbers, which matters in a habitat where any single animal can die at any moment. A female colossal squid can release millions of eggs at once, more eggs than a school gymnasium could hold if you tried to count each one individually. Most of those eggs will never survive to adulthood, but a small percentage is enough to keep an entire population alive for generations. On top of that, squid eat almost anything smaller than themselves, from fish to other squid, which means they are not stuck waiting for one specific meal to show up in a habitat where meals are already rare. This flexible diet lets them spread across a huge range of depths, from the edge of sunlight down to nearly 2 miles below the surface. Different squid species have claimed different layers of this vertical world, almost like tenants renting different floors of the same building. Some stay near the top, closer to light and warmth. Others sink into the coldest, darkest section and rarely come back up. Because there are so few large predators built specifically to hunt in this kind of cold, squid have room to grow bigger here than almost anywhere else on the planet. Bigger bodies mean more room to store energy, better protection against smaller predators, and eventually, animals so massive they barely resemble the small squid seen in a seafood market back home. Two species stand above the rest in size and reputation, each one famous in its own way, each one shaped by millions of years in this exact type of hostile water. One is long and slender, stretched out like a whip. The other is thick and heavy, built more like a torpedo than a ribbon. Both of them carry a level of mystery that most animals lost the moment humans started filming everything with a phone. A handful of smaller Antarctic squid species round out this picture too, filling in gaps at every depth like background characters in a much bigger story, feeding penguins, seals, and toothfish long before anyone ever notices them. But two names keep coming up again and again whenever scientists discuss the true giants of this frozen ocean. These two are different enough and dangerous enough that they deserve to be introduced one at a time, starting with the one most people have already heard of, even if they have never seen one alive. The giant squid has haunted sailor stories for hundreds of years, long before any scientist confirmed it was real. Grown to full size, this animal can stretch about 43 feet from the tip of its body to the end of its longest tentacles, roughly the same length as a school bus. Picture one parked next to your school in the morning, except instead of yellow paint and rows of windows, it is covered in pale, almost translucent skin, with two enormous eyes staring back at anyone who gets close. Most of that incredible length comes from two long feeding tentacles, thin and whip-like, that shoot out from the body to snatch prey from several feet away. The main body, called the mantle, is shorter and thicker, holding the brain, heart, and other organs in a shape built more like a torpedo than a snake. Giant squid live throughout the world's oceans, and the cold Southern Ocean holds a particularly healthy population of them, feeding in some of the deepest, darkest water on the planet. For decades, almost everything scientists knew about this animal came from dead specimens washed up on beaches or pulled from the stomachs of whales. Nobody had photographed one alive in its natural habitat until the year 2004, when Japanese researchers finally caught one on camera nearly a mile below the surface. Even after that breakthrough, sightings stayed incredibly rare, each one treated like a major scientific event rather than a routine encounter. 8 arms line the front of its body, each one covered in round suckers lined with tiny teeth, strong enough to leave circular scars on anything that struggles against them. Those suckers work like hundreds of tiny mouths gripping onto prey, impossible to shake loose once they clamp down. The giant squid hunts mostly by ambush, staying still in the dark water and waiting for fish or smaller squid to swim within striking range of those two long tentacles. Speed matters more than strength in this style of hunting, and a giant squid can strike faster than a human eye can follow, snapping its tentacles forward and yanking prey back toward its beak in a fraction of a second. That beak sits hidden at the center of all 8 arms, shaped like a parrot's, sharp enough to slice through flesh and bone in a single bite. For most of ocean history, an animal this size with weapons this effective would sit near the very top of the food chain, feared by almost everything smaller. Its skin can shift subtly in color and texture, helping it blend into the gloom during long stretches of waiting between meals, and its huge fins ripple gently to hold its position without wasting energy. In the Southern Ocean, that is not quite how the story goes. As big and dangerous as the giant squid is, it shares these waters with a heavier, stockier relative that many scientists consider even more formidable, an animal built less for speed and more for raw power, hiding even deeper in the cold than its slender cousin ever bothers to go. Meet the colossal squid, an animal that trades length for pure bulk. A confirmed adult female, caught by a fishing crew in the Ross Sea near Antarctica, weighed close to 990 pounds, roughly the weight of a small car sitting on a bathroom scale. Scientists believe some individuals may grow even heavier, possibly past 1100 pounds, based on squid beaks pulled from the stomachs of sperm whales far larger than any confirmed specimen caught so far. Unlike the giant squid's long, whip-thin tentacles, The colossal squid is built thick through the mantle and arms, closer in shape to a torpedo packed with muscles than a slender ribbon drifting through the water. Its total length usually falls short of the giant squid's, often somewhere between 30 and 45 feet including its arms, but pound for pound, nothing else in the invertebrate world comes close to matching its mass. Biologists refer to it as the heaviest invertebrate known to science, heavier than any insect, crab, or octopus ever recorded. This animal lives almost exclusively in the freezing water surrounding Antarctica, a habitat so remote that live sightings stayed essentially non-existent for most of scientific history. For nearly a century after the species was first identified, not a single living adult had ever been filmed in its natural deep water home. Everything researchers knew came from injured squid pulled up by accident on commercial fishing lines, already dying by the time anyone got a good look, or from partial remains found inside the stomachs of whales and seabirds. That gap in knowledge earned the colossal squid a reputation as one of the true ghosts of the ocean, a creature scientists were certain existed but could almost never observe alive. Its size alone raises questions that still do not have full answers. How does an animal this heavy move efficiently through water without burning through its energy reserves within hours? How does it hunt in complete darkness against prey that has spent millions of years learning to avoid detection? Part of the answer lies in a trick shared by several deep-sea squid species, a chemical solution built directly into their bodies that solves the weight problem before it even becomes a problem. It has nothing to do with muscle or fins. It has everything to do with chemistry most people never think about outside of a cleaning supplies aisle. Even its mantle, the thick central section holding its major organs, feels closer in shape to a torpedo packed with dense muscle than to anything resembling the soft squid found on a dinner plate. Understanding that trick means looking past the size and the reputation and getting into the actual biology hiding inside this animal's body. A system so effective that it lets a creature the weight of a car hover motionless in open water without spending a single calorie doing it. Sunlight does not travel far in the ocean, and understanding exactly where it disappears explains almost everything about how these squid live. Near the surface, down to about 200 feet, sits the sunlight zone, bright enough for plants and colorful fish, similar to the shallow end of a swimming pool on a clear day. Below that begins the twilight zone, stretching down to around 3,000 feet, where light fades to a faint blue glow and eventually to nothing at all, like walking from a sunny parking lot into a movie theater with the light slowly dimming. Past 3,000 feet lies the midnight zone, permanent total darkness that never once sees a ray of sunlight, not during the brightest summer day, not ever. Both the giant squid and the colossal squid spend much of their lives in and around this lightless zone, often diving well past 3,000 feet, sometimes closer to 6,000 feet or more. At that depth, describing it as dark barely captures the reality. It is darker than a closed closet with the door shut and a blanket thrown over the gap underneath. No moonlight reaches this deep, no starlight, no glow from a distant boat, nothing except the occasional flash of bioluminescence from another creature nearby. Living in permanent darkness creates an obvious problem for any animal that needs to find food, avoid predators, or locate another member of its own species. Most land animals rely heavily on vision, and humans in particular trust their eyes above almost every other sense. Take away all light completely, and normal eyes become nearly useless overnight. A squid trying to survive at these depths cannot simply give up on eyesight and rely on smell or touch alone, not when speed and distance matter this much in a fight for survival. Instead, evolution pushed in the opposite direction entirely, building eyes so large and so sensitive that they can pull useful information out of nearly non-existent light, catching the faintest possible glimmer and turning it into a usable picture of the surrounding water. This single adaptation explains one of the most famous and unsettling features these squid carry, a feature that looks almost alien compared to any animal found on land. It is the reason a diver's flashlight beam, weak and scattered this deep, can still catch something staring back from the darkness, two enormous eyes reflecting light from 30 feet away, before the rest of the animal's shape ever becomes visible. Researchers who have piloted submersibles this deep describe the sensation as closer to floating inside a closed eye than exploring an ocean, with the only proof of movement coming from instruments rather than anything visible outside the window. Once you understand why those eyes exist, they stop looking like a random mutation and start looking like exactly what they are. One of the most efficient light collecting tools ever built by nature, designed for a world where every photon counts. Hold a dinner plate in front of your face and picture that as a single eyeball. That is roughly the size scientists recorded on the largest colossal squid specimens ever measured, an eye stretching close to 11 inches across, the largest eye of any known animal on Earth, living or extinct. Giant squid carry eyes almost as large, sometimes measuring close to 10 inches wide, dwarfing the eyes of a blue whale despite that animal being hundreds of times heavier overall. For comparison, a human eye measures about 1 inch across, meaning a colossal squid's eye could be roughly 10 times wider than a person's, closer in scale to a basketball sitting inside a much smaller frame. Why would an animal need an eye this enormous? The simple answer involves basic physics rather than mystery. A bigger eye means a bigger lens, and a bigger lens can gather more light, similar to how a wide camera lens captures a brighter photo in a dim room compared to a narrow one. In near total darkness, every extra photon of light matters, and a massive eye becomes a massive advantage over any animal stuck with smaller, less sensitive vision. These eyes are not just large. They are packed with light-sensitive cells arranged in a pattern built specifically to detect faint movement rather than sharp, detailed color images. A colossal squid probably cannot see fine details the way a human can read a street sign from across a parking lot. Instead, it can detect subtle shifts in light and shadow from a considerable distance, catching the faint blue-green glow produced by bioluminescent creatures drifting nearby, or the shape of something large moving through the water even without direct illumination. Scientists studying giant squid eyes discovered something even more specific and unsettling. These eyes appear tuned to detect the exact wavelength of light produced by one particular type of deep-sea threat, a signal that triggers an immediate warning before danger ever gets close enough to strike. That detail turns these eyes from a simple survival tool into something closer to an early warning radar system, built by evolution over millions of years to solve one specific life or death problem. Every additional inch of eye size in these animals likely traces back to pressure from a single predator patrolling these waters. A hunter so massive and so effective that squid without adequate warning systems simply never survived long enough to pass on their smaller eyes. Some marine biologists compare this defense system to a car's rear collision sensor, quietly scanning the darkness and waiting to trigger an alert the instant something large gets close enough to matter. That predator does not chase using sight at all. It hunts using sound, sending out powerful clicks that bounce off anything solid in the darkness, turning the entire ocean into a three-dimensional map built from echoes instead of light. Understanding exactly how that hunting method works reveals why an eye the size of a dinner plate might still not be enough to guarantee survival down here. Cut open most animals and you find one heart pushing blood in a steady loop. Cut open a squid carefully and you find 3. 2 smaller hearts sit near the gills, pumping blood specifically through them to load up on oxygen, while a third, larger heart pushes that oxygen-rich blood out to the rest of the body. 3 separate pumps working together sound like overkill until you consider the problem these animals are solving. Cold water holds oxygen differently than warm water, and moving enough of it through a large muscular body takes serious pumping power, especially for an animal about to blast itself forward using jet propulsion at a moment's notice. Even stranger than the extra heart, squid blood is not red, it runs pale blue, sometimes almost clear, because it carries oxygen using a copper-based molecule called hemoxyanin instead of the iron-based hemoglobin found in human blood. Iron-based blood turns bright red when it carries oxygen, the same reaction that colors a rusty nail. Copper-based blood turns blue instead, similar to the color a penny develops after sitting outside for years. This copper-based system actually works better than iron-based blood in cold, low-oxygen water, which explains why so many deep-sea and cold water animals rely on it. It is a small design switch with a massive payoff, letting a colossal squid's blood keep functioning efficiently at temperatures that would make human blood sluggish and inefficient. 3 hearts and blue blood might sound like something pulled from a science fiction movie, but every piece of it serves a specific survival purpose, shaped entirely by the extreme environment these animals call home. None of it happened by chance, and none of it happened quickly. It took millions of years of small adjustments, generation after generation, each tiny improvement compounding on the last, until a squid's entire circulatory system became a finely tuned machine built for cold water and low oxygen. This kind of extreme specialization keeps showing up throughout the squid's body, and blood is far from the strangest example. The same pressure to survive in a lightless, freezing, oxygen-thin ocean also solved one of the biggest physical challenges facing any large animal without a rigid skeleton: the challenge of simply staying afloat. A colossal squid weighing close to 1,000 pounds cannot swim constantly for its entire life without exhausting itself completely, yet it needs to hover motionless in open water for hours at a time while it hunts. A body built entirely from muscle, the way a tuna or a dolphin is built, would eventually exhaust itself trying to fight gravity for hours on end without rest. Squid needed a different answer, one that did not depend on strength or stamina at all. Muscles alone cannot solve that problem forever. The real solution is chemical, hidden inside nearly every cell in the squid's body, and it explains why these animals feel strangely light and jelly-like whenever a fisherman accidentally pulls one to the surface. Most fish solve the floating problem with a gas-filled swim bladder, a small internal balloon that keeps them from sinking without constant effort. Squid never developed that organ, so nature found a completely different fix, one built from chemistry instead of trapped air. Deep sea squid, including the colossal squid, fill much of their body tissue with a fluid rich in ammonium chloride, a compound lighter than the surrounding seawater. Fill enough tissue with something lighter than water and the whole animal becomes closer to neutrally buoyant, meaning it neither sinks toward the seafloor nor floats toward the surface without extra effort. Think of it like a life jacket built directly into every muscle fiber, invisible from the outside but working constantly from the inside. This trick lets a colossal squid hover motionless in open water for extended periods, conserving energy that would otherwise get burned constantly fighting gravity. In a habitat where food can be scarce and unpredictable, that saved energy might mean the difference between surviving until the next meal or starving in the meantime. The trade-off is texture. This same ammonium-rich tissue gives the squid's flesh a soft, almost gelatinous quality, nothing like the firm muscle found in a fast-swimming fish such as tuna. Cut into a colossal squid, and the meat feels closer to a thick jelly than a steak, watery and loose rather than dense and fibrous. That soft, chemically loaded flesh creates an unexpected side effect that has nothing to do with buoyancy and everything to do with survival against predators. Ammonium compounds taste bitter and unpleasant to many animals, similar to biting into something that has gone sour in the back of a refrigerator for weeks. Sperm whales, the primary predator of both giant and colossal squid, still eat them constantly despite this unpleasant taste, because at these depths, options are limited and calories matter more than flavor. Smaller predators, however, often avoid heavily ammonium-loaded squid entirely, preferring species with a more neutral taste when given the choice. This means the same chemical trick that lets a colossal squid float motionless in the dark might also make it slightly less appealing to certain hunters roaming these waters, an accidental bonus layered on top of the buoyancy solution. Humans who have tried eating colossal squid meat describe a similar unpleasant, bitter aftertaste. One reason this animal has never become a commercial food source despite its enormous size. Floating easily and tasting bad might seem like unrelated features, but in the deep southern ocean, where every advantage counts towards survival, nothing about a squid's body exists purely by accident. Even the way this tissue distributes across the body matters, concentrated most heavily in areas where extra buoyancy helps the most, while denser muscle stays reserved for the arms and mantle where real strength still matters during a hunt or an escape. Every strange trait connects back to the same relentless pressure, staying alive one more day in a place actively trying to kill anything that cannot adapt fast enough to its rules. Some deep sea squid take camouflage to a level that sounds impossible outside of a magic trick. Certain species, especially in the glass squid family closely related to Antarctic squid, can turn their entire body nearly see-through, letting light pass through their flesh almost like looking through a window instead of at a solid animal. Hold a clear plastic cup up to a lamp and notice how the light passes straight through without much resistance. Now imagine an entire living creature achieving that same effect, muscles, organs, and all, floating in open water where there is nowhere to hide behind a rock or duck into a crevice. In a habitat with no coral reef to disappear into and no seafloor clutter at these depths, transparency becomes one of the few real hiding strategies available. A predator scanning the water for a solid silhouette might swim within a few feet of a transparent squid and never notice anything at all, its eyes sliding right past a shape with almost nothing to catch the light. This effect comes from specialized cells and tissue structures that either scatter light in a way that prevents a clear outline from forming, or allow light to pass through with minimal disruption, similar to how a jellyfish can seem to disappear in clear water despite floating right in front of a diver's mask. Not every part of the body can stay fully transparent all the time. Eyes present a particular challenge, because the same structures that let a squid gather faint light to see also tend to reflect or absorb light in a way that creates a visible dark spot, even when the rest of the body has gone nearly invisible. Some species solve this with special reflective tissue positioned specifically to disguise the eye's outline, essentially camouflaging the one part of the body that transparency alone cannot fully hide. This entire disappearing act takes energy and precise biological control, meaning it functions less like a constant passive state and more like an active choice the animal can adjust depending on the situation. A squid drifting calmly through open water with nothing nearby might stay transparent for long stretches, saving energy while relying on invisibility as its main defense. Even the squid's internal organs sit positioned and shaped in ways that minimize how much solid, light-blocking tissue sits in any one place, spreading mass out rather than clustering it into an obvious central shadow the way a human torso would. Divers who have encountered nearly transparent squid describe the unsettling experience of noticing only a faint outline or a slight shimmer in the water, gone the moment they blink or look away. The moment something changes nearby, whether prey to chase or a predator to avoid, that same transparency can shift almost instantly, and the reason behind that shift reveals one of the most impressive nervous system tricks in the entire ocean. Flipping from invisible to fully visible does not happen through muscle movement the way a human might flex an arm. It happens inside specialized skin cells called chromatophores. tiny sacs of pigment surrounded by a ring of muscle fibers. When those muscles contract, the sac stretches wide, spreading pigment across a larger area of skin and making that pigment far more visible. When the muscles relax, the sac shrinks back down to a nearly invisible dot, letting the transparent tissue underneath show through again almost like a window blind snapping open and shut. A squid's brain and nervous system can control thousands of these chromatophores at once, adjusting color and pattern across its entire body in a fraction of a second. A chameleon shifts shades slowly and calmly over several minutes. A squid works on a completely different timescale, closer to flipping a switch, transparent one moment and patterned the next, controlled almost like pixels lighting up on a screen. Even the timing of these changes appears deliberate rather than random, often triggered by a specific event nearby rather than shifting constantly without any clear cause. Scientists studying glass squid species have documented individuals switching between full transparency and solid, opaque coloring depending on the exact situation they face. A calm, undisturbed squid drifting through open water might stay mostly see-through, relying on invisibility as a passive defense. The moment a predator gets close enough to pose a real threat, some species can flash to a darker, more solid appearance almost instantly, possibly as a startled response meant to confuse an attacker for the split second needed to escape. Others do the opposite, going even more transparent under threat, essentially doubling down on invisibility rather than abandoning it. Either strategy demonstrates a level of active, moment-to-moment control over the animal's own appearance that few other creatures on the planet can match. It functions like a costume the squid can put on or take off at will, adjusted moment to moment depending entirely on what danger or opportunity happens to be swimming nearby, rather than a fixed pattern locked in place for life. Controlling the system requires a nervous system fast enough and precise enough to coordinate an enormous number of tiny muscles across the entire body simultaneously, all while also managing 8 arms, 2 tentacles, and a jet propulsion system built for sudden bursts of speed. High-speed camera footage of related squid species captured in laboratory tanks shows entire color patterns rippling across the body in well under a second, faster than most human reflexes could ever manage on purpose. That level of coordination raises an obvious question. How does an animal with no centralized skeleton and a body built mostly from soft tissue manage to think and react fast enough to survive a habitat this unforgiving? The answer involves a brain unlike almost anything found in the rest of the animal kingdom, one that solves the coordination problem in a way no vertebrate ever developed. A human brain sits alone inside the skull, sending out commands and waiting for signals to travel all the way down the arms and legs before anything happens. A squid's nervous system works nothing like that. Roughly 2/3 of a squid's neurons, the specialized cells that carry electrical signals, do not sit in the central brain at all. They live directly inside the arms themselves. Each arm carries its own local processing power, capable of reacting to touch, adjusting grip, and coordinating movement without waiting for a signal to travel all the way to the brain and back. Picture 8 separate helpers, each one smart enough to make quick decisions on its own, all reporting back to a central manager but not needing permission for every single small task. This setup allows a colossal squid to control 8 arms and 2 long tentacles almost simultaneously, gripping prey with some arms while others continue reaching, curling, or adjusting position independently. In a fast-moving fight against slippery prey or a much larger predator, waiting for every single movement to be approved by a central brain would be far too slow. Decentralized control solves that speed problem directly, letting each arm react to what it feels in real time rather than waiting for instructions from headquarters. The brain itself sits in an unusual location and shape compared to almost every other large animal. Instead of a rounded organ safely tucked inside a skull, a squid's brain forms a ring wrapped directly around its esophagus. The tube food travels through on its way to the stomach. This means every bite a squid swallows technically passes through the middle of its own brain. a detail that sounds uncomfortable but works perfectly fine for an animal built this differently from the vertebrates. This brain structure supports impressively complex behavior for an invertebrate, including problem solving, memory, and the split-second coordination needed to control chromatophores, jet propulsion, and grasping arms all at once during a hunt or an escape. None of this complexity exists for show. Every part of it serves the same relentless goal that shapes everything else about these animals, staying alive and successfully feeding in one of the most hostile environments on the planet. A squid with slow reflexes or poor coordination simply does not survive long enough to grow to full size in water this cold, this dark, and this dangerous. The animals that do survive to adulthood, the ones stretching the length of a school bus or weighing as much as a small car, represent millions of years of that same brutal filtering process, keeping only the fastest, smartest, and best coordinated individuals alive long enough to reproduce. Researchers studying related octopus species, close cousins that share the same decentralized nervous system, have documented individual arms continuing to react to touch for a short time even after being separated from the main body. A strange but useful window into just how independent this system really is. With a body this well equipped for hunting and self-defense, the next question becomes obvious. What weapons does a colossal squid actually carry into a fight, and how do they compare to anything else swimming in these waters? Life slows down when the water gets cold enough. Chemical reactions inside every living cell, the tiny processes that break down food and produce energy, happen more slowly in cold temperatures than in warm ones. The same reason a refrigerator keeps food fresh longer than a kitchen counter. For an animal living in water hovering near the freezing point almost year-round, this creates both a challenge and an advantage at the same time. The challenge is obvious. Muscles fire more slowly, digestion takes longer, and every physical action costs more time to complete, compared to an animal living in warm tropical water. A colossal squid cannot move with the same explosive burst speed as a smaller squid living in a sun-warmed reef near the equator, at least not for sustained periods. The advantage is less obvious but arguably more important for long-term survival. A slower metabolism means an animal needs less food overall to stay alive, stretching out the time between meals in a habitat where meals can be difficult to find. Some deep-sea squid species may go weeks between substantial feeding events, surviving on stored energy reserves built up during rare successful hunts. This slower pace of life likely contributes to how large these animals can grow. Many cold water and deep-sea species across the animal kingdom tend to grow larger than their warm water relatives, a pattern scientists call deep-sea gigantism. Bigger bodies lose heat more slowly relative to their size, similar to how a large pot of soup stays warm longer than a small cup of the same soup left out on a counter. Bigger bodies can also store more energy reserves, useful padding against the unpredictable feast or famine rhythm of life in these depths. Slower growth over a longer lifespan may allow colossal squid to reach sizes that would take an impossibly short amount of time to achieve if attempted at a warmer, faster metabolic pace. Nobody knows for certain how long a colossal squid can live, since almost no individual has ever been studied continuously from birth to old age, but some researchers suspect a lifespan considerably longer than the 1 or 2 years typical of many smaller, warmer water squid species. Every extra year of life in this cold, slow-paced environment means more time to grow, more time to gather size and strength, and more time to become the kind of animal capable of standing its ground against a predator many times its own body weight. A slower heartbeat, a slower digestion, and a slower pace of daily life all add up to an animal built for endurance rather than a short, explosive burst of activity, closer in spirit to a marathon runner than a sprinter. Slow does not mean weak here, it means patient, efficient, and built for the long game in a habitat that punishes anything wasteful. That patience matters even more once you consider the second major physical challenge facing every animal at these depths, a challenge that has nothing to do with temperature and everything to do with the sheer, invisible weight of the ocean pressing down from every direction at once. Drop a sealed empty water bottle from a boat and let it sink far enough, and the water pressure will crush it flat long before it reaches the bottom of the deepest parts of the Southern Ocean. Rigid, air-filled structures do not handle deep sea pressure well, because the air inside gets compressed while the water outside keeps pushing with unstoppable force. This is exactly why submarines need thick metal hulls engineered specifically to resist collapsing under that pressure, and why those hulls become heavier and more expensive the deeper a vessel needs to travel. A colossal squid solves the same problem in a completely different way, and the solution comes down to one simple fact about its body. It has no rigid skeleton at all, no bones, and almost no large air-filled cavities that could get crushed the way a submarine hull might fail under pressure it was not built to handle. Instead of fighting the pressure with a rigid structure, a squid's soft water-filled tissue allows pressure to pass through its body almost freely, equalizing on the inside just as fast as it builds on the outside. There's nothing solid inside to crush, no trapped air pocket to compress, no rigid frame to buckle under the strain. This is similar to the difference between throwing a rock at a solid wall versus throwing that same rock into a pool of water. The wall might crack or break, but the water simply moves out of the way and closes back in without lasting damage. A squid's entire body functions closer to that second example, flexible enough to let extreme pressure pass through without causing structural failure. The one hard structure inside a squid's body, its beak, sits embedded within soft muscle tissue specifically because a completely rigid mouth would create exactly the kind of pressure problem the rest of the body was built to avoid. Even the beak stays relatively small and dense rather than large and air-filled, minimizing any weak point where crushing pressure could cause damage. This pressure-tolerant design lets colossal squid comfortably patrol depths that would instantly kill an unprotected human diver and would seriously threaten even a well-built submarine without proper reinforcement. Depth beyond 1 mile, sometimes closer to 2 miles, becomes simply another neighborhood for these animals rather than a dangerous extreme they must fight to survive within. Combine this pressure tolerance with the slow, patient metabolism built for cold water, the giant light-gathering eyes tuned for total darkness, and the ammonium-rich tissue solving the buoyancy problem, and a clear picture starts forming. Every single trait scientists have documented in this animal connects back to the exact same set of extreme conditions, cold, dark, and crushing, working together like pieces of a single, cohesive survival strategy. Engineers designing deep sea equipment sometimes study exactly this kind of natural pressure tolerance for inspiration, trying to copy nature's solution instead of relying purely on thicker and thicker metal shells that grow heavier with every added layer of protection. A body this well engineered for defense against the environment itself would be impressive enough on its own. What makes the colossal squid genuinely dangerous, however, is not just its ability to survive down here. It is the specific weapons built into its arms, weapons that set it apart even from its already fearsome cousin, the giant squid. A giant squid catches prey with suckers, hundreds of them lining its 8 arms and 2 tentacles, each one ringed with tiny hardened teeth that bite into flesh once the sucker clamps down. That alone would earn respect from anything unlucky enough to get caught. The colossal squid raises the stakes considerably. Instead of relying only on suckers, its arms and tentacles are lined with sharp, curved hooks made of a hard material similar in toughness to a fingernail, though far more rigid and pointed. Picture the difference between grabbing something with a hand covered in small suction cups versus grabbing it with a hand covered in fish hooks. One method holds on through suction and friction. The other method physically pierces and locks into whatever it touches, making escape dramatically harder once contact happens. These hooks appear along the 2 long tentacles in especially high concentration, positioned exactly where the squid needs maximum grip, while reeling struggling prey back toward its beak. Some of these hooks also line the shorter arms closer to the body, adding an extra layer of grabbing power once prey gets pulled in close during the final stage of an attack. Scientists examining preserved colossal squid specimens have measured individual hooks reaching over a third of an inch in length, small compared to a shark's tooth, but more than sharp enough to tear through the flesh of a fish or another squid without much resistance. Marine biologists dissecting preserved arms under laboratory lighting have counted well over 20 individual hooks on a single tentacle club alone, each one angled slightly differently to maximize coverage across the widest possible surface area during a strike. Multiply that single hook by the dozens lining just one arm, then multiply again across 8 arms and 2 tentacles, and the total grabbing power becomes difficult to overstate. Preserved specimens stored in museum collections still carry these hooks intact decades after capture, hard and sharp enough that researchers handle them with the same caution they might use around a box of fish hooks or sewing needles. Nothing caught within reach of a colossal squid at full strength gets free through simple wriggling or thrashing. The hooks are curved specifically to dig in harder, the more a trapped animal struggles against them, similar to how a fishing hook becomes more difficult to remove the more it gets pulled against instead of pushed with the direction of the barb. Evidence suggests these hooks can rotate and swivel at the base, giving the squid active control over grip angle and direction rather than relying purely on a fixed, static hook shape, turning what might look like a passive trap into something the squid actively steers. That single detail changes everything about how dangerous this weapon actually becomes in a real struggle, and it deserves its own closer look before moving any further into this story. A fixed hook works well enough on its own, but a rotating hook solves a problem that has nothing to do with grip strength and everything to do with control. The hooks lining a colossal squid's arms and tentacles sit on small swiveling bases, allowing each individual hook to rotate independently rather than staying locked in one fixed direction. Imagine a grappling hook that could twist and reposition itself the instant after it caught onto something, adjusting its angle automatically to dig in deeper no matter which way the target tried to pull away. That flexibility means prey struggling against the grip cannot simply twist free by finding the one angle where the hook loses its bite, because the hook itself moves and adjusts along with the fight. Combined with the sheer number of hooks covering both tentacles and arms, this creates a weapon system built less like a single trap and more like dozens of small, independently adjusting traps working together at once. Fishermen who have accidentally caught colossal squid on long baited lines describe deep, circular wounds left behind on their equipment and occasionally on the fish they were trying to reel in themselves, evidence of exactly how aggressively and effectively these hooks engage with anything they touch. In fact, one of the strangest and most repeated stories from Southern Ocean fishing crews involves colossal squid stealing bait and even hooked fish directly off long commercial fishing lines before the crew ever gets a chance to reel their catch to the surface. These squid appear to target Patagonian toothfish specifically, a large, slow, deep water fish that fishing operations around Antarctica regularly target using long lines baited across miles of open ocean. A struggling toothfish, already hooked and unable to swim away at full speed, becomes an easy target for a colossal squid patrolling nearby, essentially turning a fisherman's own bait and equipment into an unintentional dinner bell. Crews have reported reeling in lines only to find toothfish stripped down to bare bones, or occasionally finding a colossal squid itself still tangled in the gear, refusing to let go of a stolen meal even as it gets hauled toward the surface against its will. This behavior reveals something important about how these animals actually hunt in the wild, beyond simply lurking motionless in open water waiting for something to drift by. They appear opportunistic and aggressive, willing to investigate an easy meal even when that meal comes attached to human fishing equipment they have never encountered before in their evolutionary history. Fishing crew members working these long lines for years sometimes learn to recognize the specific pattern of damage a colossal squid leaves behind, distinct from the cleaner bite marks left by sharks or the simple missing hooks left by a fish that simply wriggled free on its own. That same aggressive, opportunistic instinct becomes far riskier once the target shifts from a struggling toothfish to something considerably larger, more dangerous, and far more determined to win the encounter. A predator patrolling these same waters with weapons and senses built specifically to hunt animals exactly this size. A sperm whale can hold its breath longer than almost any other animal on the planet, diving over a mile beneath the surface and staying down for more than an hour before finally returning for air. Picture a school bus-sized body, powered by a heart the size of a small refrigerator, plunging straight down into total darkness on a single breath, deeper than most military submarines are rated to travel. Adult sperm whales regularly reach depths past 6,000 feet in search of food, occasionally diving even deeper, entering the exact same lightless world where colossal and giant squid spend most of their lives. Sperm whales evolved specifically to hunt in this exact environment over millions of years, and squid make up the overwhelming majority of their diet, with a single adult whale eating an estimated 1 ton of squid or more every single day, just to maintain its massive body. Multiply that number across an entire population of sperm whales feeding constantly throughout the Southern Ocean, and the sheer scale of squid being hunted becomes almost impossible to fully picture, easily numbering in the millions of individual animals consumed every year. Reaching these depths on a single breath requires physical adaptations most mammals simply do not have. A sperm whale's lungs can collapse safely under pressure without causing damage, unlike a human lung, which would be seriously injured under the same conditions. Its blood and muscle tissue can store enormous reserves of oxygen, similar to carrying extra fuel tanks that release oxygen gradually throughout a long dive rather than needing to breathe constantly like a surface-dwelling animal. Its heart rate slows dramatically once submerged, sometimes dropping to a fraction of its surface. Resting rate, conserving oxygen for the organs that need it most during the hunt. Scientists tracking these dives with satellite tags have watched whales descend at a steady, controlled pace, conserving energy on the way down so more of it remains available once the actual hunt begins near the bottom. All of this biological engineering exists for one primary purpose: giving the whale enough time underwater to locate, chase, and successfully capture squid living at depths no sunlight ever reaches. Finding prey in complete darkness, however, requires more than just the ability to reach these depths. Vision becomes almost useless this far down, even for an animal with reasonably good eyesight, which means a sperm whale cannot simply look around and spot a squid drifting nearby the way a human might spot movement in a dimly lit room. Researchers tracking tagged sperm whales have recorded individual dives lasting close to 2 hours in some extreme cases, an almost unbelievable stretch of time to spend without a single breath of air. Instead, sperm whales rely on an entirely different sense, one built around sound rather than light, turning the pitch-black ocean into something they can navigate and hunt through almost as effectively as if the water were perfectly clear. Clap your hands inside an empty room and listen to how the sound bounces off the walls, giving a rough sense of the room's size and shape even with your eyes closed. Sperm whales use a far more advanced version of that same basic idea to hunt in total darkness. Deep inside a sperm whale's massive, block-shaped head sits an organ scientist called the spermaceti organ, filled with a waxy substance the whale uses to focus and direct powerful clicking sounds out into the water ahead of it. These clicks rank among the loudest sounds produced by any animal on Earth, loud enough that a human standing too close in the water could theoretically feel real physical harm from the pressure wave alone. Once these clicks leave the whale's head, they travel outward through the water and bounce off anything solid enough to reflect them, including the dense, muscular body of a colossal or giant squid drifting nearby. The whale listens for those returning echoes using tiny differences in timing and intensity between each ear to build an extremely detailed picture of its surroundings, similar to how a bat navigates a completely dark cave using echolocation, just scaled up dramatically for use underwater across much greater distances. This method does not depend on light at all, meaning it works exactly as well in the pitch-black midnight zone as it would in a fully lit swimming pool. A sperm whale can likely detect the size, distance, and even some details about the shape of a squid, long before it ever gets close enough for the squid's own senses to detect the whale in return. This creates a serious imbalance in the encounter before it even begins. The squid's advanced eyesight, built specifically to catch faint light and detect bioluminescent flashes, offers little advantage against a predator that never needed light in the first place. Some researchers suspect this exact imbalance explains why squid eyes evolved to be so sensitive to the specific wavelength of light produced by disturbed bioluminescent plankton, since a massive whale swimming through the water at speed would inevitably stir up these tiny glowing organisms along its path, creating an accidental warning sign visible even in complete darkness. In other words, the squid may actually be detecting the glowing trail of disturbed plankton the whale leaves behind as it approaches, rather than the whale itself, buying just enough extra warning time to attempt an escape. Some researchers describe the whale's clicking system as closer to a natural sonar array than a simple sense, precise enough to distinguish between a squid and a similarly sized rock formation on the seafloor from a considerable distance away. Even with that warning, escape does not always succeed. When a hunt ends in contact rather than a clean escape, the encounter can turn into a genuine physical struggle between two enormous, powerful animals, and the evidence of exactly how violent that struggle can get is written permanently across the skin of nearly every adult sperm whale swimming these waters. Look closely at the skin of almost any adult sperm whale and a pattern emerges that has nothing to do with age or sun damage. Circular white scars, often clustered in the dozens or even hundreds across the head and body, mark places where something grabbed on and refused to let go without a fight. These circular marks match the exact size and spacing of squid sucker rings, sometimes even showing the smaller puncture marks left by hooks in cases involving a colossal squid rather than the smooth suckered giant squid. Scientists studying these scars can often estimate the approximate size of the squid involved just by measuring the diameter of the individual scar rings, since larger squid carry proportionally larger suckers and hooks. Some scars measured on sperm whales suggest an originating squid considerably larger than any specimen ever caught, and confirmed by researchers, hinting that truly massive individuals may exist somewhere in these waters, animals that have never been seen, filmed, or measured by any scientific team. Every scar tells a small story of survival, both for the whale carrying it and, in some unknown number of cases, for a squid that managed to escape a hunt it should have lost. A whale does not develop these scars by passively swallowing prey, the way a person might swallow a grape without much resistance. These marks form because the squid actively fought back during capture, wrapping its arms and tentacles around whatever part of the whale it could reach and gripping tight enough to leave a lasting, visible mark even after the encounter ended. Considering the sheer size difference between these two animals, a sperm whale stretching 60 feet or more against a squid measuring a fraction of that length, the fact that squid leave any mark at all says something important about the intensity of these underwater confrontations. It plays out as a genuine physical fight, brief but violent, far closer to combat than to a clean, one-sided ambush, with a smaller, soft-bodied animal managing to inflict real, lasting damage on something many times its own size and weight, before ultimately losing the larger battle for survival. Marine biologists have spent years studying these scar patterns specifically because direct observation of an actual hunt remains almost impossible to capture on camera, meaning scars represent some of the best physical evidence available for understanding exactly how these underwater battles typically unfold. Photographers documenting these whales during surface encounters often focus entire projects specifically on cataloging scar patterns, treating each whale's skin almost like a fingerprint unique enough to help identify and track individual animals across multiple sightings over the years. What these scars cannot fully explain, however, is exactly how often the squid manages something even more surprising than simply leaving a mark, actually surviving the encounter entirely and living to grow larger for another attempt at a very different outcome. A single scar might just mean one unlucky encounter, but most adult sperm whales carry dozens, and researchers studying this pattern found something that changes the entire picture. Many of these whales show scars in different stages of healing, some old and faded to a pale gray, others fresh and still pink, proving that individual whales survive many separate encounters with large squid, spread across years or even decades of their lives, rather than just a single close call. This turns each whale's skin into something close to a written record, a timeline of repeated confrontations stretching back through much of its life story. Marine ecologists studying sperm whales and their squid prey recently pulled together decades of the scattered scar evidence into a single, formal picture of what they now describe as a long-running underwater conflict, one that has quietly shaped both species for millions of years without most people ever realizing it was happening. According to that research, this rivalry stretches back roughly 34 million years, to the point in evolutionary history when early toothed whales first developed echolocation and started hunting in deep, dark water using sound instead of sight. Before that shift, squid mainly needed to avoid predators that hunted using vision, which meant camouflage and color-changing tricks like transparency offered a reliable defense. The moment whales started hunting by sound instead, that entire defensive strategy became far less effective, forcing squid to develop new countermeasures over the following millions of years, including the massive light-gathering eyes capable of detecting an approaching predator by the faint glow of disturbed plankton rather than sound. Every giant eye, every hook, every scar left behind on a whale's skin represents one small part in this much longer, slower story, an evolutionary back and forth where each side kept adapting in response to pressure from the other, neither one ever fully winning the conflict outright. Whales developed increasingly powerful sound-producing organs and improved deep-diving physiology. Squid developed sharper hooks, better warning systems, and, according to some researchers, a strategy of retreating even deeper as they age, since every additional bit of depth adds extra difficulty and time cost for any whale trying to follow. This kind of long, slow, mutual arms race rarely produces a clean winner, and this one appears no different. Both species remain locked in the same basic pattern today, millions of years after it started, playing out silently in total darkness every single day across the Southern Ocean without a single human witness present for most encounters. Some researchers even describe this dynamic using the language of an actual arms race, borrowed from military history, since each generation of squid and whale essentially inherits small improvements from the last, compounding slowly across an almost unimaginable stretch of geological time. Understanding this deep evolutionary context makes one particular squid survival strategy stand out as especially clever, a strategy that has nothing to do with fighting back at all, and everything to do with a simple biological limitation every whale shares no matter how powerful it becomes. For all its size, power, and advanced hunting senses, a sperm whale shares one unavoidable weakness with every other mammal in the ocean. It breathes air, and no matter how impressive its lungs and oxygen storage might be, that air eventually runs out. A dive lasting over an hour sounds incredible compared to a human, who typically cannot hold a breath for even 2 full minutes, but it still represents a hard limit the whale cannot ignore no matter how badly it wants to continue a hunt. Every minute spent chasing a squid deeper into the abyss is a minute closer to the point where the whale must turn around and swim back toward the surface for air, whether or not it has successfully caught its prey. This single fact creates one of the only real escape strategies available to a squid facing a hunt it cannot win through strength or speed alone. If a squid can survive long enough, staying just out of reach or absorbing an attack without being fully captured, it only needs to outlast the clock the whale is racing against rather than the whale itself. Retreating even deeper works directly in the squid's favor here, since sperm whales already operate near the outer limit of what their bodies can handle during a single dive. Every additional 100 feet a squid descends adds extra time and oxygen cost for a pursuing whale. Extra time the whale may not have left before its own body forces it back toward the surface regardless of how close it came to catching its meal. This explains part of why deep-sea gigantism and depth preference in these squid species may connect directly back to predator pressure from whales, since individuals capable of surviving and hunting at greater depth gain a real, measurable survival advantage against a predator constrained by its own need to breathe. It also helps explain why so many battle scars appear on whales rather than ending every single encounter in a clean kill. Some fraction of these confrontations likely end with the whale running low on time and oxygen, forced to abandon the chase and surface for air, while an injured but still living squid disappears back into the darkness below, carrying fresh wounds of its own that heal slowly over the following months. This dynamic mirrors a simple rule familiar to anyone who has ever played a timed game, where surviving the clock matters just as much as outplaying the opponent directly. Nobody knows the exact success rate for squid attempting this specific escape strategy, since almost no one has ever directly observed the full hunting sequence from start to finish in the wild. What scientists do know is that colossal and giant squid populations remain healthy enough to sustain the enormous appetite of the entire sperm whale population, feeding across the Southern Ocean year after year, which strongly suggests this deep water strategy works often enough to keep the species going, despite constant, relentless pressure from one of the ocean's most capable predators. A newly hatched colossal squid measures barely larger than a grain of rice, drifting near the surface in relatively shallow water alongside countless other tiny plankton and larvae. At this stage of life, it looks almost nothing like the massive, hook-covered predator it will eventually become, small enough that a single gulp from a passing fish could end its life before it ever gets the chance to grow. Survival at this size depends heavily on staying near the surface layers, where food in the form of even smaller plankton remains abundant and relatively easy to catch without needing much strength or speed. As the squid grows larger over the following months and years, it gradually shifts its preferred depth downward, moving away from the busier, more heavily hunted surface layers and into progressively deeper, colder water. Scientists studying this pattern believe the shift happens gradually rather than all at once, with young squid found at moderate depths, subadults found deeper still, and only the largest, oldest individuals found down in the true abyss where adult colossal squid are believed to spend most of their time. This gradual descent likely serves multiple purposes at once. Deeper water offers fewer predators capable of threatening a squid that has already grown too large for most surface-dwelling hunters to handle. It also offers access to different prey, including the slow-moving, deep water fish like Patagonian toothfish that make up a significant part of an adult colossal squid's diet. Younger, smaller squids simply are not physically capable of hunting these larger prey items yet, making the shallower zones with smaller prey a better fit until they grow enough size and strength to handle bigger meals further down. This means a colossal squid effectively experiences several completely different habitats throughout a single lifetime, starting in relatively bright, food-rich, shallow water and ending in permanent, crushing darkness nearly 2 miles below the surface. Few animals on the planet undergo this dramatic shift in habitat and lifestyle across their lifespan, comparable to a person spending their childhood in a busy city center before eventually retiring to complete isolation somewhere far from any other living neighbor. This pattern also explains why scientific understanding of the species remains so incomplete even today. Different life stages require entirely different research methods and equipment to study properly, and most expeditions can only reasonably access one depth range at a time. A team studying juvenile squid near the surface might never encounter an adult, while a team searching the deep abyss for adults would have already missed observing the same individual during its earlier, shallower years. Tracking a single individual across this entire journey would require decades of continuous observation, something no research program has ever managed to accomplish for this particular species, given how rarely any life stage gets spotted at all. This exact gap in knowledge made a certain scientific breakthrough in the year 2025 feel less like a routine discovery and more like a genuine milestone decades in the making. For roughly 100 years after scientists first identified the colossal squid as a distinct species, not one single living adult or juvenile had ever been captured on camera in its own natural habitat. Every piece of evidence came from dead or dying specimens, remains pulled from stomachs, or scars left behind on the skin of whales. That entire century-long gap finally closed in March of 2025, during an expedition in the South Atlantic Ocean near the South Sandwich Islands, an extremely remote chain of islands even by Antarctic standards. Researchers aboard a research vessel operated by the Schmidt Ocean Institute were piloting a remotely operated submersible nearly 2,000 feet below the surface, part of a broader survey project searching for new and rarely seen ocean life in this isolated corner of the Southern Ocean. As the submersible descended through the water column, something drifted directly into view on the live camera feed, small, pale, and almost translucent, floating calmly rather than fleeing from the bright lights and unfamiliar machine suddenly sharing its water. Scientists monitoring the footage in real time immediately recognized this as something unusual, though confirming the exact species required careful frame-by-frame analysis afterward, rather than an instant, on-the-spot identification. Specific features helped make that final identification possible, including a distinctive set of hooks positioned along the middle portion of its arms, a detail unique to colossal squid and absent in similar-looking relatives. One researcher reviewing the footage later described feeling genuinely overwhelmed with excitement upon spotting those hooks clearly for the first time, aware immediately that the team was witnessing something no human being had ever documented before in over a century of searching. This moment mattered for reasons beyond simple novelty. Confirmed, direct observation of a living colossal squid in its natural environment gave researchers their first real opportunity to study actual behavior, rather than relying entirely on second-hand evidence pieced together from remains and scars. How does this animal move through open water? How does it react to unfamiliar light and machinery nearby? Does it display any of the transparency and camouflage tricks documented in related glass squid species? Every one of these questions suddenly had at least a partial, direct answer for the very first time in scientific history. News of the sighting spread quickly through the marine biology community once the footage was confirmed, treated by many researchers as one of the most significant cephalopod discoveries in decades, on par with the earliest confirmed footage of the giant squid captured roughly 2 decades earlier. Yet this landmark discovery also came with an unexpected twist, one that reminded everyone involved exactly how much more remains completely unknown about this species even after such a historic breakthrough. The animal caught on camera during this expedition was not the massive, fully grown predator most people picture when they hear the word colossal squid at all. The squid captured on camera during that historic 2025 expedition measured only about 1 foot long, roughly the size of a house cat, rather than the school bus-sized giant most people imagine when picturing a colossal squid. This was a juvenile, likely still years or even decades away from reaching anything close to full adult size, filmed at a depth of about 2,000 feet, considerably shallower than the depths adults are believed to eventually reach later in life. For a species so heavily associated with extreme size, seeing this small, delicate-looking individual drifting calmly in front of a research submersible created an unusual mix of excitement and gentle disappointment among some viewers expecting something more immediately dramatic. That reaction, however, misses exactly why this specific sighting mattered so much to the scientists actually studying the species. A juvenile this size, confirmed and documented with clear video evidence, fills in a critical missing piece of the colossal squid's full life story, one that researchers previously had to guess at using indirect evidence and comparisons to related species. Before this footage existed, nobody could say with total confidence exactly what a young colossal squid looked like while alive and swimming naturally, how it moved, or how it behaved when confronted with something unfamiliar nearby. This footage answered several of those questions at once. The juvenile displayed a calm, largely stationary posture, rather than an aggressive or panicked reaction to the approaching submersible, floating with its arms held loosely rather than fleeing immediately. Researchers noted its body appeared largely transparent, consistent with the camouflage strategy documented in other glass squid relatives, suggesting this defensive trick likely develops early in life rather than appearing only once a squid reaches full adult size. Comparing this footage carefully against previous knowledge, researchers confirmed the animal was almost certainly less than a year old, based on its small size and the still developing proportions of its arms relative to its mantle. Every detail like this adds another small piece to a puzzle that scientists have been slowly assembling for over a century, using nothing but scattered fragments. A single juvenile squid caught briefly on camera might seem like a small discovery next to the scale and mystery surrounding this entire species, but in a field where confirmed direct observations remain this rare, even a small discovery carries enormous scientific weight. News outlets around the world picked up the story within days, many running headlines describing a baby sea monster finally caught on camera, a framing that captured public attention, even though most scientists preferred a far less dramatic, more careful description of the actual find. This same expedition season produced a second remarkable piece of footage as well, involving an entirely different, closely related species that shares many of the same extreme camouflage tricks, captured displaying an unusual and rarely documented defensive behavior that few researchers had ever witnessed in person before that moment. The colossal squid shares its frozen habitat with a smaller, stranger relative called the glacial glass squid, an animal that pushes the transparency trick discussed earlier to its absolute limit. Where a colossal squid uses its see-through tissue as one defense among several, the glacial glass squid appears to rely on it as a primary survival strategy, keeping its body almost entirely clear for most of its life, rather than switching between transparent and solid coloring depending on the situation. Researchers working on a joint expedition between institutions in the United Kingdom and Germany, exploring the remote Bellingshausen Sea near Antarctica, captured the first confirmed footage of the species alive in its natural deep water habitat, another milestone achieved during roughly the same period as the colossal squid discovery. Spotting an almost fully transparent animal against the equally dark, featureless background of deep ocean water presents an enormous challenge even for trained researchers actively searching for it with bright lights and high-resolution cameras. The team credited careful, patient observation during a slow, controlled descent for eventually catching a clear glimpse of one drifting calmly through their camera's field of view. Once identified, The footage revealed additional details about how this species moves and behaves that had never been documented before. Because so little is known about several closely related squid species inhabiting these waters, distinguishing one from another sometimes comes down to small, specific physical details rather than obvious visual differences, requiring genuine expertise built over years of studying preserved specimens and rare photographs. Every new piece of confirmed footage like this helps build a clearer picture of exactly how many distinct squid species actually share this extreme habitat, a number that continues shifting as new discoveries and genetic studies refine what scientists once assumed was a much simpler picture. Water clarity, current, and the total absence of any natural light all work against a camera crew in these conditions, meaning even a successful expedition might spend days searching before capturing a single usable frame of footage. Antarctic and deep southern ocean waters may host a far greater diversity of large, specialized squid species than researchers previously realized, each one occupying a slightly different depth range, hunting strategy, or physical adaptation suited to this specific type of extreme cold water environment. The joint nature of this expedition, combining universities and research institutes from multiple countries, reflects how expensive and technically demanding this kind of Antarctic research has become, requiring specialized ships, trained pilots, and equipment capable of handling both the cold and the pressure at once. This growing recognition of hidden biodiversity matters beyond simple scientific curiosity, because it reshapes how researchers think about the entire food web supporting sperm whales, seals, and seabirds throughout this region. Before moving further into the story of exactly how these animals behave when threatened, one particular defensive posture documented during recent expeditions deserves closer attention. A strange, almost ritualistic looking pose that multiple glass squid species appear to share. During that same Bellingshausen Sea expedition, researchers watched the glacial glass squid perform a behavior scientists have nicknamed the cockatoo pose, named for its resemblance to the way a cockatoo bird raises the crest of feathers on top of its head when startled or excited. Instead of feathers, the squid raises all 8 of its arms straight up and slightly backward, holding them loosely above its head in a position that looks almost relaxed, despite happening in what should be a high-stress encounter with an unfamiliar, deep-sea vehicle. This pose has been documented before in a small handful of other glass squid observations, though rarely enough that each new sighting adds meaningfully to scientists' understanding of what the behavior might actually mean. Researchers currently have several competing theories, rather than one confirmed explanation, an honest gap in knowledge that reflects exactly how little direct observation exists for these deep water species overall. One leading idea suggests the pose may serve a defensive purpose, possibly making the squid's silhouette appear larger or more confusing to a potential predator approaching from below, similar to how some animals puff up or raise their fur to appear more intimidating when threatened. Another theory suggests it could relate to buoyancy control, with the raised arm position possibly helping the animal maintain a stable, balanced position in the water column during a period when it wants to remain as still and undetected as possible. A third possibility involves simple curiosity or investigation, with the squid raising its arms specifically to better sense an unfamiliar object nearby using touch-sensitive cells concentrated along the arms, rather than relying purely on its eyes. Without more confirmed footage captured across a wider range of situations, researchers cannot yet say for certain which explanation, if any, fully captures why this behavior exists. What makes this particular observation valuable, regardless of the final answer, is simply how rare the opportunity to witness it at all remains. Every confirmed sighting adds another data point toward eventually solving this small mystery. building slowly toward a more complete answer, the same way each individual scar on a sperm whale's skin adds one more data point toward understanding the larger predator-prey relationship discussed earlier. One researcher on the expedition reportedly described feeling a rush of pure excitement watching the arm slowly rise on the live camera feed, aware in real time that the team was capturing something almost nobody had ever properly documented before. Direct behavioral observation like this represents some of the most valuable and hardest to obtain information in all of deep-sea biology, requiring advanced technology alongside patience, timing, and a considerable amount of luck. Behavior, however, only tells part of the story. To understand how scientists piece together everything else known about these elusive animals before modern submersible technology existed, the story has to shift toward a far less glamorous but equally important source of information, one found by cutting open the stomach of the very predator hunting it rather than by watching a living squid at all. Long before any submersible camera ever captured a living colossal squid, scientists had already learned an enormous amount about the species using an unlikely source: the stomach contents of dead sperm whales examined during old whaling operations and later strandings. A squid's beak, the one truly hard structure in its entire body, does not fully digest the way soft tissue does. It survives inside a whale's stomach long after the rest of a meal has broken down completely, sometimes accumulating in large numbers as a whale continues feeding over months or years without ever passing every single beak out of its system. Researchers examining these stomachs found beaks representing colossal squid far larger than any complete specimen ever caught and measured directly, evidence that genuinely massive individuals exist somewhere in these waters, even though nobody has ever seen one alive. Beak size correlates closely enough with overall body size in squid that scientists can estimate an individual's original length and weight using careful measurements and mathematical comparisons based on smaller, fully measured specimens. Using this method, some researchers have suggested certain beaks recovered from sperm whale stomachs may have come from squid weighing well over 1,000 pounds, larger than any confirmed specimen on record. Beaks are not the only useful evidence recovered this way. Small fragments of skin, sucker rings, and hooks occasionally survive digestion long enough for researchers to study as well, offering additional physical details that help confirm species identification and provide small clues about age, health, and even recent injuries the animal may have sustained during its life. This method of study, sometimes called indirect biology, played an enormous role in shaping scientific understanding of the colossal squid throughout most of the 20th century, essentially allowing researchers to reconstruct a rough picture of an animal's life using nothing but the leftover evidence of its death. It comes with obvious limitations. A stomach full of beaks cannot reveal how an animal moves, hunts, or behaves while alive, and it certainly cannot answer questions about coloring, camouflage, or social behavior the way direct video footage eventually could once that technology became available. Still, this patient, indirect detective work built the essential foundation that made everything scientists know today possible, filling in size estimates, geographic range, and population details long before a single research submersible ever descended into Antarctic waters carrying a working camera. Museum collections around the world now hold thousands of these recovered beaks, carefully catalogued and measured by generations of researchers who dedicated entire careers to a species they had never once seen alive, piecing together a portrait built entirely from leftovers. Combining this old-fashioned evidence with new direct observations paints one of the more complete pictures scientists have ever assembled for such an elusive species, though several major gaps remain, including questions about exactly how these animals recover from injuries sustained during violent encounters with predators many times their size. Losing an entire arm in a fight against a sperm whale would end the story for most animals, either through a fatal blood loss or through a permanent crippling disadvantage that makes future hunting nearly impossible. Squid, including both giant and colossal species, belong to a group of animals capable of regenerating lost limbs to a meaningful degree, similar to the well-known ability of an octopus to regrow a missing arm after losing one to a predator or a serious injury. Regrowing an arm takes considerable time and energy rather than happening overnight, full and perfect the way it might in a movie, and the new limb does not always match the original in exact length, strength, or hook placement, especially if the animal is already an adult when the injury occurs. Younger squid, still actively growing toward their full adult size, appear to regenerate lost or damaged limbs more completely and efficiently than fully mature adults, another possible advantage tied to the extended gradual growth period discussed earlier in this story. For an animal engaged in an ongoing, millions of years long conflict with a predator as powerful as the sperm whale, this regenerative ability functions as a critical safety net. An encounter that leaves a squid alive but missing part of an arm or a section of tentacle torn away during a desperate escape does not necessarily end that individual's chances for future survival and reproduction the way a similar injury might for many other animals. Blood flow to the injury site increases dramatically during the early stages of this process, delivering the raw nutrients and cellular material needed to slowly rebuild muscle, skin, and eventually the hardened hook structures themselves. Scientists examining preserved specimens have occasionally found individuals with visibly regrown or unevenly matched arms, physical evidence of a past injury that the animal survived and recovered from well enough to continue living normally afterward. This detail adds an important layer to the earlier discussion about scars and survival, extending the story beyond a single dramatic encounter and into a longer view of an animal's entire life. A colossal squid reaching truly enormous adult size may well carry the physical evidence of multiple close calls throughout its lifetime: healed wounds, unevenly regrown arms, and scars from encounters it barely survived, each one adding to a growing picture of resilience built through repeated exposure to genuine life-threatening danger. This process draws on the same basic biological toolkit that lets a starfish regrow a lost limb or a lizard regrow part of its tail. An ancient survival trick refined over millions of years across many completely unrelated branches of the animal kingdom. This resilience helps explain how a species facing constant, relentless predation from one of the ocean's most capable hunters has managed to persist for millions of years without ever going extinct. It also helps explain something else entirely: the origin of centuries-old sailor stories describing enormous sea monsters capable of dragging entire ships beneath the waves. Legends that turned out to be far closer to real biology than most people ever expected. Sailors have told stories about massive sea monsters lurking beneath the waves for as long as ships have sailed the open ocean, and one legend in particular stands out for how closely it eventually matched real biology. The Kraken, a gigantic tentacled creature said to rise from the deep and drag entire ships beneath the surface, appears in stories stretching back centuries across multiple cultures near the North Atlantic. For most of that time, scientists dismissed these tales as pure exaggeration or fantasy, the kind of story a frightened sailor might invent after months at sea with too little sleep. That dismissal became harder to maintain once actual giant squid specimens started washing ashore or getting hauled up in fishing nets during the 19th century, providing undeniable physical proof that an enormous tentacled ocean animal genuinely existed, even if it rarely, if ever, behaved anything like the ship-destroying monster from the old legends. A giant squid stretching over 40 feet long, complete with powerful gripping arms and a sharp tearing beak, would have looked utterly terrifying to any sailor encountering one at the surface, whether during a genuine attack or simply as a dead or dying animal floating in the water after being injured by something else entirely, such as a sperm whale. It becomes easy to imagine how a brief, frightening encounter with an injured giant squid thrashing at the surface, combined with limited scientific understanding and a natural tendency to exaggerate a dramatic story, could gradually transform over generations into tales of a monster, large and powerful enough to sink entire ships. The colossal squid likely contributed to these legends as well, even though it stays in far deeper water than its more surface-active relative and gets seen at the surface even less often. Its sheer weight and powerful hooks would have made an equally strong impression on any crew unlucky or lucky enough to encounter one, whether alive, dying, or already dead and floating. Modern science has not fully debunked every detail of these old legends so much as it has found the real, biological animal hiding underneath centuries of exaggeration and fear. The kraken was never purely imaginary. It was a genuine massive predator, just smaller and less aggressive toward ships than the old stories claimed. Its reputation inflated by fear, distance, and the natural human tendency to make an already impressive animal sound even more impossible. Old ship logs and sailor journals from those centuries occasionally describe encounters in vivid, frightening detail. Arms wrapping around a small boat or a strange, glowing shape rising just beneath the surface at night, details that read very differently once modern biology explains exactly what such an animal could and could not actually do. Even with modern science firmly separating myth from biological fact, one part of the original legend remains stubbornly, genuinely true today. An animal this large, this well-armed, and this rarely seen still manages to escape direct human observation almost entirely, especially once it reaches its full, true adult size. Every confirmed sighting of a colossal squid described so far in this story, from the historic 2025 video footage to the largest specimens ever caught by fishing crews, shares one important detail in common. None of them represent a fully grown, maximum size adult confirmed alive and healthy in its natural deep water habitat. The juvenile filmed in 2025 measured about 1 foot long, still extremely early in its decades-long journey toward adulthood. The largest confirmed specimens caught by fishing operations, including the roughly 990-pound female pulled from the Ross Sea, were already dead or dying by the time researchers got a proper look, injured during the process of accidental capture on a long fishing line never designed to handle an animal this size and strength. Evidence from whale stomach contents suggests even larger individuals exist, potentially significantly larger than any specimen measured so far, yet not one of these theoretically bigger squid has ever been directly observed, captured, or measured by any scientific team in history. This gap represents one of the most persistent mysteries remaining in modern marine biology, especially remarkable considering how much underwater exploration technology has advanced over just the past few decades. Researchers now have access to remotely operated submersibles capable of reaching crushing depths, high-resolution cameras built specifically for low light conditions, and increasingly sophisticated methods for tracking and predicting where deep-sea animals might be found. Despite all of that progress, a fully grown adult colossal squid living naturally at its true maximum size has still never appeared on camera, never been tagged, and never been directly studied while alive. Several factors likely combine to explain this ongoing gap. True adults may spend almost their entire lives at depth deeper than most research expeditions typically explore, staying well below 2,000 feet in areas that remain expensive and logistically difficult to survey regularly. Their overall population, while healthy enough to sustain heavy predation from sperm whales, may still be relatively small and widely scattered across an enormous stretch of remote ocean, making a random encounter statistically unlikely even with modern equipment actively searching. Some researchers also suspect these animals may be naturally cautious or evasive around unfamiliar objects like a submersible, actively avoiding bright lights and mechanical noise rather than drifting calmly into view the way the smaller, less experienced juvenile did during that landmark 2025 sighting. Some scientists compare the search for a fully grown adult to searching for a specific person somewhere across an area larger than the entire continental United States, except the search also has to happen in total darkness, under crushing pressure, using equipment that can only stay down for a few hours at a time before needing to resurface. Whatever the exact combination of reasons, the result remains the same. Somewhere in the freezing, crushing darkness of the Southern Ocean, a fully grown colossal squid weighing potentially over 1,000 pounds is almost certainly alive right now, patrolling water no human camera has ever managed to capture it within, waiting for an encounter that may not happen for years, decades, or possibly ever. The colossal squid enjoys a level of legal protection most animals never receive, though not because of any dedicated conservation campaign or endangered species listing built specifically around it. It lives almost entirely within the boundaries covered by the Antarctic Treaty System, an international agreement signed by dozens of countries that limits commercial activity and protects the broader Antarctic environment as a whole. Because of this, and because of how remote and inaccessible its deep water habitat remains even for modern fishing operations, the colossal squid faces essentially no direct threat from human hunting or commercial harvest, unlike countless other ocean species facing serious pressure from overfishing around the world. This protection exists almost by accident rather than by careful design, a side effect of Antarctica's broader legal status rather than a targeted effort built around this specific animal. Scientists still cannot say with any real confidence how large the total colossal squid population actually is, since no reliable survey method currently exists for accurately counting an animal that spends most of its life in nearly inaccessible deep water spread across an enormous stretch of remote ocean. Population estimates rely heavily on indirect methods, including calculations based on how many squid an entire regional population of sperm whales would need to consume every year just to survive, then working backward to estimate how large the underlying squid population must be to sustain that level of predation without collapsing. These indirect estimates suggest a population large enough to remain stable for now, but they come with significant uncertainty, and scientists have limited ability to detect a genuine decline until it has already progressed significantly. This uncertainty carries real consequences reaching far beyond the colossal squid itself. As a major food source for sperm whales and likely other predators including certain seabirds and seals feeding on smaller squids encountered near the surface, colossal and giant squid help support the entire predator structure of the Southern Ocean food web. Fisheries scientists monitoring toothfish populations nearby have started factoring squid predation into their own models as well, recognizing just how tightly connected every species in this ecosystem really is, from the smallest plankton to the largest whale. A serious decline in squid population, whether from climate change altering water temperature and prey availability, or from broader ecosystem disruptions still not fully understood, could ripple outward and threaten species that depend on a stable, reliable food source in one of the harshest environments on the planet. Unlike whales, tuna, or countless other ocean species targeted directly by commercial fishing fleets around the world, no market or industry has ever developed around hunting colossal squid specifically, leaving it in the unusual position of being both largely unstudied and largely unthreatened at the exact same time. Protecting a species scientists barely understand presents an unusual challenge, one that depends on continuing exactly the kind of research described throughout this entire story, patient expeditions, careful indirect evidence, and rare hard-won direct sightings, each one adding another piece to a puzzle still far from complete, even after more than a century of dedicated scientific effort. Humans have mapped the surface of Mars in far greater detail than they have mapped the floor of their own ocean. Scientists estimate that more than 3/4 of the deep-sea floor remains completely unmapped at any useful resolution. A strange fact considering people have lived on this planet's surface for hundreds of thousands of years, while the ocean covering most of it stays largely unexplored. Antarctica's surrounding waters rank among the least studied regions within that already massive knowledge gap, thanks to extreme weather, dangerous ice, brutal cold, and a level of remoteness that makes even routine research expeditions expensive and logistically difficult to organize. Every confirmed discovery described throughout this story, the first footage of a living colossal squid, the first sighting of a glacial glass squid, the detailed scar-based research connecting squid and sperm whales across millions of years of shared evolution, happened only within the past few years, made possible by relatively recent advances in submersible technology, camera systems, and international scientific cooperation. This timing reflects a genuine turning point in ocean exploration technology rather than mere coincidence, one that finally allows researchers to reach depths and conditions that remained essentially impossible to study directly for most of scientific history. Similar breakthroughs keep happening across other parts of deep ocean research as well, with new and previously unknown species discovered on nearly every well-funded deep-sea expedition that goes looking. Some of these discoveries involve entirely new species never previously documented in any form. Others involve confirming direct sightings of animals long known only through indirect evidence, exactly like the pattern seen throughout the colossal squid's own scientific history. This pattern suggests something important about how much more remains genuinely unknown across deep ocean life as a broad category, squid very much included. If an animal as large as the colossal squid, potentially weighing over 1,000 pounds at full size, managed to avoid direct scientific observation for over a century, it raises a reasonable question about what else might be hiding down there. Animals perhaps even larger, stranger, or more specialized than anything documented so far. Universities and independent research institutes have also started pooling resources across national borders more often than in past decades, recognizing that no single country can realistically fund an Antarctic expedition alone, given the extraordinary costs involved. Every technological improvement in submersible design, camera sensitivity, and expedition funding effectively opens a slightly wider window into a world that has remained almost completely hidden from human eyes for the entire history of our species. Funding agencies around the world have started paying closer attention to this pattern in recent years, gradually increasing support for polar and deep-sea research after decades of relatively limited investment compared to space exploration budgets. Antarctica's deep water specifically continues offering some of the most promising and most challenging opportunities for exactly this kind of discovery, a genuine frontier still largely untouched by direct human observation, despite sitting right here on our own planet rather than somewhere impossibly distant in space. Everything covered across this entire story, the crushing pressure, the near-freezing water, the giant dinner plate ice, the swiveling hooks, the ammonium-filled tissue, the scars written across a sperm whale skin, all of it points toward the same final idea. The Antarctic deep sea did not create gentle, simple creatures. It created some of the most specialized, extreme, and genuinely dangerous predators found anywhere on this planet. Animals shaped by millions of years of relentless pressure into something that barely resembles the small, harmless squid most people picture when they hear the word at all. A colossal squid drifting silently through total darkness right now, somewhere beneath the Southern Ocean, carries every single one of these adaptations at once. A floating, hook-covered, giant-eyed survivor built specifically for a world that would kill almost anything else within minutes. The sperm whale hunting it carries its own equally impressive set of adaptations, evolved over the exact same millions of years in direct response to the squid's own defenses, each species pushing the other toward greater size, better senses, and more effective weapons in a silent underwater competition that started long before humans ever existed to witness it. Somewhere out there right now, a fully grown adult colossal squid, larger than any specimen ever measured, is almost certainly alive, carrying scars from encounters no camera has ever recorded, hiding in water colder and darker than most people will ever experience in their entire lives. Juvenile glass squid are drifting near the surface this very moment, invisible against the pale morning light, slowly beginning that same decades-long journey toward the crushing depths below. Somewhere, a sperm whale is diving past 6,000 feet on a single breath, clicking into the darkness, searching for a shape its ears can find long before its eyes ever could. This entire hidden world keeps operating every single day, whether or not a single human being ever manages to witness it directly. That thought alone should be enough to fundamentally change how anyone looks at the ocean going forward. Every hook, every scar, every giant eye tuned to catch a single stray photon exists for the exact same reason. A species refusing to disappear, despite conditions that should have wiped it out generations ago. It is not simply a large body of water sitting between continents. It is one of the last genuine frontiers left on this entire planet, home to animals more strange, more specialized, and more resilient than almost anything found on dry land, existing in near total secrecy just a few thousand feet beneath ships, research stations, and coastlines full of people who have no idea exactly what continues, drifting silently in the darkness directly beneath them. The next major discovery might already be swimming down there right now, waiting patiently in the cold and the dark for the day a camera finally arrives to see it.